This is the second part of the presentation about the reflections and the use to model objects bouncing off any kind of obstacles. So this time we'll look at a practical problem like there is a surface, a sloped surface, like an obstacle, and we have an object hitting this surface at this position with some velocity v. Knowing the normal vector which defines the slope of this surface, the task is to calculate the final velocity vector v prime, which will be here. So the real trajectory of this object is of course somewhere here, so the object is flying this way. Here it is hitting the surface, and then it will follow v prime, the final velocity. This vector here shows the the initial velocity, the velocity of this object in the moment when it hits the obstacle. By now we know the formula for the final velocity, which is the initial velocity v minus 2v dot n. V here is once again the velocity, and n is the normal which defines the slope of this of the surface here. V dot n is a number, so to make it a vector we need to multiply it by n once again. Please note that these two multiplications are quite different. This is the dot product, dot multiplication, and this is simply multiplication of a vector by a number. So we will apply this formula to a particular problem presented here. To make it more practical, let's assume that this normal here, let's say n is minus 0.6, 0.8. These are nice numbers because squared will provide the value of 1. So as you can notice, 0.6 squared is 0.36 plus 0.8 squared is 0.64. Together it is 1. So this normal vector is indeed a normalized vector. It is the vector of the length 1. And what kind of velocity may we have here? Let's say it's 2, 1. So a practical problem is we have a slope. The slope is defined by the normal minus 0.6, 0.8, and the object hitting the surface is traveling with the velocity 2, 1. The question is, what's the final velocity? And this final velocity v prime is equal, according to the formula, to v, but v is, we know the value of v. Value of v is 2, 1. Okay? Minus 2. I will calculate this dot product using a simple and easy to use method. Should be minus 0.6, 0.8. These are the coordinates of the vector n, and these are coordinates of the vector v. Minus 0.6 times 2 is minus 1.2, and 0.8. I've just noticed that this velocity here on our picture is going slightly down, so these coordinates will be rather 2 minus 1. Okay, so I will add the minus here. Sorry for this confusion. Okay. So our velocity is 2 minus 1. 2 minus 1. 0.8 times minus 1 is minus 0.8. Adding both values, minus 1.2 plus minus 0.8, it's minus 2. So our dot product of both vectors, this vector and this vector, is actually minus 2. And this needs to be multiplied according to the formula by the normal vector minus 0.6, 0.8. This equals 2 minus 1, minus 2 times minus 2 is plus 4, so plus 4 minus 0.6, 0.8. And this equals, once again, 2 minus 1 plus 4 times minus 0.6, it's 2.4 minus 2.4. You are allowed to use a calculator. 4 times 0.8, it's 3.2. 3.2. And from this we nearly arrive to the result. 2 minus 2.54, it's minus 0.4, comma, minus 1 plus 3.2, it's 2.2. And this is the answer. This is the v prime, the final velocity, the velocity after hitting the obstacle. It is minus 0.4, 2.2. Looking at the picture here, it is quite possible it will be minus 0.422. The picture is very far from being perfect. But there is actually an easy way to find out if the result is good or not. I will use a calculator in my iPhone, and I will do a very simple calculation. I need the scientific calculator. I will calculate firstly the magnitude or length of the initial velocity. It's 2 squared plus 1 squared. It's nothing to calculate, especially here it's 5, okay? So the magnitude of the velocity or speed before the collision is square root of 5. Okay, why I calculated this? Because this collision, this event here, should not or must not change the speed of the motion. So if I now calculate the magnitude of this vector, which I'm doing right now, we also should get square root of 5. So it's 0.4 squared plus 2.2 squared equals 5, exactly. So it's square root of 5. So it's a very, very good hint that we didn't do any mistake during these calculations, because the magnitude of this vector v prime and the initial velocity v is the same, exactly as it should be. What would happen if we had a different velocity here? Like instead of 2 minus 1, minus 2, 1. What's wrong with this velocity? Something really wrong, because this velocity, minus 2, 1, will be velocity like this. That's the vector of the velocity vector of our object in the moment of hitting this surface. What it means? This means that this object is actually flying away from the surface. In this case, all these calculations wouldn't make any point, because we actually don't have any kind of a collision here with this kind of velocity. This means one very important thing. I will just present one simple calculation. When we did the previous result, the velocity of the object which was going inside this obstacle. Okay, so this was the velocity. I made the calculation of the dot product, and the result was -2. So let's repeat the calculation now. For the data we currently have, it's the normal vector, and this time we have -2, 1. Minus 0.6 minus 2, it's 1.2. This 0.8 added together, it's 2. And here is exactly where is our problem. This is positive dot product. Positive dot product means that the n vector, the normal vector, and the velocity vector are pointing in the same direction, like this. If they are pointing in the same direction, what you can recognize in this picture very easily, it simply means that this object is flying away from the surface. Okay? So to talk about reflections, about bouncing, our objects bouncing off, we have to ensure, first of all, that the normal of the surface and the velocity vector are pointing into two different directions, like this. Okay? Normal, velocity. If normal is one side, velocity is another side, this means that the object was actually flying into the obstacle and has a chance to bounce off. So in this case, the calculation of p prime does have this sense. In any other case, there is a mathematical, strictly mathematical sense of calculation, the reflection vector, because for this vector it would be probably something like this, but it has absolutely no physical meaning. Okay? If something is flying here, it will definitely not go inside the obstacle this way. This means that if you are ever asked to calculate the velocity after hitting the surface, the first thing that you should do is to calculate the dot product v dot n, something that you will use in this formula very, very soon, the very next step. So you first calculate this dot product. If this dot product is positive, first, this is end of the story. There is nothing else to calculate because there was no collision. Okay? The object is flying away from the obstacle, not going to hit. And only if this is negative value, in case of a negative value, you simply apply this formula here, being sure that this v dot n here is a negative number. What these two cases mean in computer graphics. In computer graphics, particularly in dynamic simulation, so in what you are actually doing in games, if v dot n is negative, that's fine. This means that you have just detected a hit and you have to model bouncing, the object bouncing off a surface. If it is positive, the most likely answer is that you've just done it in the previous frame of animation. So something was flying to the obstacle, okay? In the previous frame of animation you changed the direction of the flight, and now, let's say 1/60 second later, you try to do the same thing again, but you shouldn't because this object has already been bounced off. In computer graphics, there is quite often the problem, unless you do this essential test in your programming, it may happen that an object that you model, when it should bounce off from a surface, it's magnetic, I didn't know. When it tries to bounce off from the surface, you will firstly calculate the reflection, which would create a bounce off or final velocity vector this way, but in the very next frame, you would calculate the same thing again with the velocity going inside into depth of this obstacle, and this actually makes exactly what you can see here. The object becomes stuck at the surface of the obstacle. So instead of simply bounce off from the obstacle, it will get stuck here because you will every second frame calculate this formula for a positive, and every second frame for the negative dot product of these two vectors. In effect, this object will be shown inside, will be firstly bounced off, but 1/60 of a second later it will be put inside the obstacle, and outside, bounce off, go back, bounce off, go back, bounce off, go back. The effect is like this. It will be stuck at the surface. So if you do this kind of calculation, for example, let's say take this mad idea in an in-class test. Okay, if you have something like in the in-class test, the first step to do is to calculate this dot product, check whether it is positive or negative. If it is positive, done. If it is negative, just go on with this formula, get the result.